Hello, my name is Brian Robison. I am Chief Evangelist here at Blackberry, and today we are going to take a look at artificial intelligence and specifically how it's applied within cybersecurity, and we're going to discuss a lot of elements about how it works. In today's session, we're going to begin by defining some concepts around artificial intelligence and machine learning. We're going to look at in a general sense, how do machine learned models actually work. We're then going to take that theory and apply it to some cybersecurity questions. And then finally, we're going to take a look at specifically the BlackBerry approach using AI and how we apply it to cybersecurity. So I think you're going to enjoy the session today, and thank you very much for taking your time and attending. So as I said before, we're going to begin by taking a look at some very general concepts, and I think we should start with this excellent quote by Maximilian Cohen. Math is the language of nature. Everything around us can be understood and represented by numbers. If you graph the numbers of any system, patterns emerge. Therefore, there are patterns everywhere in nature. And why are patterns important? It's because patterns allow us to predict the future. We can actually use these previous examples to draw intelligence and actually predict the future. So where does this pattern or where does this math fit in? Well, this leads us to machine learning, which is essentially a branch of artificial intelligence that allows us to develop algorithms that allow computers to evolve based it evolves their behavior based upon the data that it's given, not based upon rules. And it's this self-evolution or governance that allows these, computers and allows these algorithms to actually seem somewhat intelligent. Another way of looking at this is that the computers actually get the ability or have the ability to learn to perform a task. We don't have to tell them what to do. They actually find out how to do it from some data. Again, it's not rule based, and it's actually good at solving some fuzzy type of problems. A great example of this is a demonstration that shows how with machine learning you can actually have a computer learn how to win at a video game. It simply requires time for the video game to the player to play, and every time it fails it says, okay, don't do that again, try something else. And it only has a certain number of rules that it can follow, like jump, move left, move right, duck, those kind of things. So it just keeps going through all of the iterations until it finds a path that allows it to achieve the goal that it's trying to get to. Another way to get kind of a visual representation of the difference kind of between AI versus machine learning versus statistics is a simple Venn diagram like this, where you can see that artificial intelligence and statistics overlap, but machine learning actually kind of overlaps both of them. And machine learning is a little bit heavier in the statistics side of the world because we're trying to use machine learning to make decisions based upon the data. And what kind of decisions are we trying to make? Well, it kind of matters depending on the type of machine learning that we're trying to utilize. So there's really two types. There is supervised machine learning and there is unsupervised machine learning. And really, the difference is whether or not or how much humans get involved in this. Supervised machine learning is a really easy way to make a simple binary decision. Is this a dog or a cat? Or is this good or bad? And it's designed to essentially differentiate samples into different distinct categories. With supervised machine learning, it requires humans or some definitive example of truth, right? It requires the knowledge of someone to say this is a cat or this is a dog. Different from that, unsupervised machine learning essentially does not start with a truth. It's not trying to pattern match. It's not trying to say good or bad or dog or cat. It's only trying to associate similarities of samples to each other. It could create all kinds of different categories based upon similarities of the sample of data that it's working with. And because it doesn't start with a ground truth, humans get involved in the analysis and the efficacy of how that resulting model actually decides how the different data should be categorized. So now we have a basic understanding of the different types of machine learning. Let's take it through a theoretical use case of detecting malware, right? So we can begin by defining the objective of detecting malware. So we begin by collecting data, which is samples of software. We can divide those samples then into a good and a bad category. We can extract all of the features that we want, and that basically is what makes a file good or bad. We let the model run through the data and categorize. Then we analyze and evaluate the outcome. This essentially lets multiple models fight to the death and finds the best results. It is then published for use and testing out in the world, and we continually monitor and operate those models to see how well they are working. And sometimes we actually release smaller, newer models, we call them centroids, that actually append the main model. Essentially, we can have these miniature brains that actually go out into the field and make that main model even smarter. And there are examples of machine learning and artificial intelligence all around us, from our voice assistants to providing us, suggestions on what we watch, suggestions on route paths with maps. All these different elements are already out there that we're dealing with on a daily basis. So let's switch gears out of theory and get into some actual applications around using machine learning in cybersecurity. And if you think about the cybersecurity industry, we collect tons and massive amounts of data on malware, on intrusions, logs. All of this different information is gathered by this industry and put into our big databases. And how do we best put all of this data to work? Can we actually use this massive amount of data that we're gathering to actually make intelligent decisions? And does that yield a more kind of mainstream adoption of machine learning in the field of cybersecurity? Let's go back to our primary use case of malware detection, right? We're going to use machine learning to see if we can detect malicious software. So we need to be able to, identify, can we tell if a script or an executable or a document, if it's malicious or not? You know, Many security vendors have these massively large data sets of good and bad software, and they're oftentimes categorized as good and bad, right? They're labeled. And so, can we actually use these pre-labeled samples to actually train a classifier? And that's essentially the idea here, right? So if we want to detect what is good and bad, we need to have a massive corpus of data of good and bad. Now, just having a large, massive data set is only the start. The first phase that we have to do is we actually have to begin extracting what are called features. Now, if we were doing a machine learning model on telling the difference between a dog and a cat, the type of features we're going to be looking for are, you know, fur. Does it have fur? Does it have eyes? Does it have four legs or two legs or one leg? And those types of features are how we begin to build the library necessary to identify, is it a dog or is it a cat? Now, in malware detection, we need to look at different types of features in the actual file itself. Things like the size of the file, what strings are in the file, what metadata is there, what DLLs is that file, is that code in that file going to call? What even functions, what functions from each DLL does it call? Are parts of it encrypted? Are parts of it compressed, etc.? And then we also have the concept of dynamic features that watch the program after it's allowed to execute. So, what API functions does it call? Is it talking to the network? Is it talking to specific areas of the network? Is it reading and writing files or removing registries? What other types of dynamic behavior does it actually have once it's running? So now that we know what features to look for, we can use analysis to look at static analysis and dynamic analysis with malware, right? So static analysis looks at the file before it executes. Essentially, the goal would be to stop the malware before it's even allowed to execute, thereby causing absolutely no damage. The great thing about this is it can happen extremely quickly within, the speed of computers, within milliseconds. However, it can miss obscured information, right? Because that information is hidden, it's compressed, or it's encrypted, and it can't see that. And that's where sometimes dynamic analysis comes in. This is after the file begins executing. What type of behavior are we actually looking for? And the problem is if we use machine learning at this point, while it might be quick, the system still is compromised. It's still a victim, and it is slower because it requires that software to be actually executing on the system. And we even see examples every day of malicious files that are out there that actually take advantage of this and may you know run good code long enough to get to the point where essentially the dynamic analysis engine times out or says, I haven't seen anything bad, I'm going to then go ahead and let you run. Another example that is often seen is where malware can, short circuit or circumvent if they detect they're being watched. A lot of times, we execute malware in virtual machines. So sometimes malware won't run if it's run on a virtual machine. It actually requires physical access to the hardware and it requires a physical machine, and it can actually decide not to run the bad code. So sometimes even the dynamic analysis elements actually fail. Now, if we take a look at Blackberry's continuous approach to machine learning, we rotate the cycle slightly where we start with publish. We have a model that's out there. We monitor it to make sure that it can protect the endpoints. And our new objective is to confirm that the threats out there are actually being blocked. So we can collect additional executables that are out there in the world. These are files that maybe the machine learning model actually did not detect. And we can then prepare that data and decide upon it, categorize it, vectorize it, develop the new model based upon those new files, train it through the process of the deep neural network learning, and then analyze and evaluate, again fighting, the models fight against each other to produce the best one that actually then gets released to the world. Another way to look at this is through animation. So we begin essentially by collecting our repository of good and bad. We then break all of the features apart. We extract all of those features out of the files that we need to determine good or bad. We then map those. We statistically map those and vectorize them and train a model based upon that data and those features, and then break them into classifications of good and bad. Now let's take a deep dive into the actual feature extraction portion. So we begin with files. We actually start with greater than 1 billion files in the corpus. And we take an individual file and we break it down into different sections of interest that we're going to look at. And in those sections of interest, we examine more than 1.4 million features. So if you're looking at a dog or a cat, you might only need to see maybe 3, 4, 5 features to know the difference between a dog and a cat. But in malware, we need to look at millions and millions of features to identify sometimes what is good and what is bad. And sometimes even the lack of a feature, the non-existence of something that makes a file good actually can produce something that makes it bad. We then take that information and convert it into something that the computer can understand and actually then use as its as its rules, or as its, if we go back to playing a game analogy, its up, downs, left, rights kind of pool of available things to look at when trying to make the determination of good or bad. So, how are you able to determine kind of how good or bad different approaches of machine learning are? Well, let's go through the DARPA 3 AI waves of describe, categorize, and explain, and go through actually, there are 5 generations of machine learning. The first generation of machine learning is where only a small sample set of features are available and only a small set of samples, relatively small. And they're handpicked by humans, they're hand labeled by humans, and it generates kind of that first initial machine learning generation that is relatively easy to create results that work, but it's not very robust. It has a lot of false positives. It's able to quickly identify things, but not very accurately. And now we move into the second generation of machine learning. This is still a cloud trained model, but now we add the ability to do local prediction. So the model can actually be containerized and put down on the endpoint. And of course, we're using more features and more samples, again, human labeled. And this is, again, it's very quick, it's easy to use, and it's getting better at its robustness. It has fewer false positives, but it still makes a lot of mistakes because it's simply looking for easily interpretable patterns. Now, moving into phase 3 or generation 3, this is where we get into what we call cloud enhanced models, where the local model on the computer is still handling all of the conviction and all of the main processing, but it's enhanced by learning that happened in the cloud. And it's in this generation where we get to the point where we trust the model well enough to actually let it do the primary conviction out at the endpoint and use the cloud as a backup rather than using only the cloud for the lookup and conviction. Moving into the fourth generation, this is where we begin to see some really high level advancements where we can begin to actually train our ML models based upon data that is only out on the endpoint. We don't need the huge vast repositories that are in available and only in the cloud. We actually can begin doing some active learning on that endpoint, and human providing feedback locally on the endpoint. Is this correct or is this wrong? And this gets to a point where things begin to get really hard, as far as the ability to bypass or get around a lot of that machine learning, because we're actually learning what's on the endpoint as it's being done, as it's being used. Finally, moving into the fifth generation is where we get into the why, essentially. We get to a level of where the AI model can actually explain in like human understandable formats of why it makes its decision, not in a machine readable only format. So this is where we get to actual, potentially actual intelligence, actual, decision making, and the ability to explain why the decision is made. Perhaps an easier way to understand the generations is to look at the generations of a human. Phase 1 being that first generation, the essentially, using automated rules for the computer to follow in each unique situation. This is more akin to the traditional AV vendors that are out there that build signatures. Now, those signatures may be built upon, by ML, but it's built with very specific rules. It's looking for very specific things and doing specific actions. So essentially, this is like in the infancy of using machine learning. Now, as we grow up, we go into phase 2, where we've learned based upon rules, we've learned behavior, we've learned some different elements, and we still need our hive mind. We still need our cloud to make these decisions essentially. And this is kind of where the next generation, AV and EDR players are, where there's generic machine learned rules to find commonalities. And in this case, it's a toddler. We're walking around now. We're making some decisions, but the quality and the accuracy aren't there. It's better than being an infant, but we're not up to the point yet where we can actually make decisions upon and by ourselves. We're not autonomous yet. Phase three, generation three, is where we get into those kind of teenage years. We start to be able to shift from relying 100% on the cloud or our parents to more making our own decisions, making them out in the field where those decisions are quicker and begin to impact us better. Right? So we do some cloud learning, but we're offline conviction. We can either use the cloud or we can use our local decision making to make those decisions. So kind of like a teenager, if you will. Our fourth phase in our fourth generation, okay, now we're a full grown adult. We're able to learn new things and make those decisions at the time that it needs to be made. It's out there on the endpoint, it's making those decisions right there, real time. It learns and it makes decisions out there. Next is phase five. This is the wise grandparent that's out there, and they are able to now teach us why those decisions get made, right? So they're able to lean on their experience and be able to translate that for the younger generations, but most importantly for the humans out there that need to understand why the AI or the ML made that decision. And if you look at this, Blackberry is the only cybersecurity vendor that can actually offer phases 3 through 5. Phase 3 was where we began back in 2012 with Silence Protect, and it was able to actually make its decisions autonomously on the endpoint. We then added Silence Persona, which actually gets the ability to actually create its machine learning on the endpoint as the user is doing its work. It's learning your behavior, how you touch the mouse, how you move the mouse, how you type keys, how you type words, how you touch the touch screen of your phone. What features of the program do you commonly use? What processes do you normally start? It's able to develop and actually build the machine learned model on the endpoint based upon the data that it's gathering. And as all of this data comes into a consolidated place, then BlackBerry Solutions will be able to actually provide you contextual understanding of why those different machine learning models made their decisions and provide you with the evidence and things like that that are necessary for the human to understand why those decisions were made. And why is it that BlackBerry is able to do this? Well, it's because we essentially invented the use of machine learning in cybersecurity. In fact, Silence and BlackBerry hold more AI and ML cybersecurity patents than any other company in the world. So you may, ask yourself why? What does this matter? Why does it matter that Silence and BlackBerry contain, the lion's share of the AI and ML use in cybersecurity? Well, it matters because protection is the most important aspect of cybersecurity. And here's a great example of how we can actually predict malicious software. And in this slide, you can see all of these different, brand name samples of malware, if you will, and how many months ahead of when those samples were actually seen in the real world by the cybersecurity industry did our AI prevent it. And how did we do that? Well, what we do is we actually take the sample of malware as it comes out and we test it against older brains, older AI models, older machine learned models, and we find out exactly how old of a version of our software detect and block that sample of malware from running. And as you can see here, the many months ahead of when that malware became known to the public world, did Silence and Blackberry actually prevent it from running? And this prediction capability actually allows us to prevent organizations out in the world from becoming victims. And if you'd like to learn more about how we apply AI and machine learning to cybersecurity, go check out our Introduction to Artificial Intelligence for Security Professionals we produced. It's available out there and it's a great read. Again, my name is Brian Robison. I'm with Blackberry. Thank you very much for your time. Prevention of cybersecurity attacks is actually possible, and I really encourage you to ask Blackberry how. Thank you.